All right, so yeah. As you have on your schedule here, there's not going to be a homework for this Tuesday coming. This topic is going to take us a little while to cover, so I want to make sure we have plenty of time, and then we'll do homework set number 10 a week from today, then, Thursday. So hopefully that'll all make sense between now and then. Questions? Probably. Yeah, there's yours. Mariah, I've got yours. And what's the other? I have a lot of tests, but I don't have a lot of students. Okay. So, any questions about the schedule or anything like that? Okay. Wow, it feels cold here. Regular. All right. So, there's something that I said a while back, and that is that samples are not active. And I talked about sample variation. Why is that a problem for us? What problem does that create when we have sample variation? Well, in order for that to create a problem, we would have to know what we're actually trying to do. What are we actually trying to do? What's our purpose in getting a sample? We want to understand a population. And so because we have sampling variation, then we have a problem with understanding the sample. Or the population, sorry. Yeah, I had some caffeine. Probably not enough. So sampling variation means that every time I go out there and make a measurement, it's not actually telling me what I want to know, because what I want to know is about the population as a whole, and I don't have that information. However, I am able to control this. And if I can control this, then that will eliminate some of this uncertainty. If I can control the sampling variation, then that means when I get my sample, I will be able to use the sample to know something. about the population. Let me give you an example. Let's say that somebody says to you, for a algebra class, we expect the age of the people to be somewhere around 24 years old, 25 years old for a certain kind of algebra class. And if I walk into an algebra class and everybody is over 50, then I would say, there's something going on here. This is different. This is unusual. But when somebody says, you know, the ages in your class are going to be somewhere around 25 years old, that doesn't mean that everybody's 25. Certainly there's some variation, right? And if I say, what's the average for this class or that class? It might be 27, it could be 22 or whatever else, but it's not going to be 50. That would be an unusual result, right? We just talked about this last time. I can tell from my sample what would be an unusual result. And if I get an unusual result, then that tells me something has changed, something that's different. Okay? So I want to be able to understand how this variation can be controlled. Well, we just went through this whole thing, right? With the X bar and all that different kind of stuff. But what we're going to use then, and I also said this, a single number estimate is not helpful. And remember, I said this was the measure of the center. And I said it was sideways. If I go out and I make some kind of a measurement and I find out something about the center of my data, that doesn't really help me necessarily. It doesn't really tell me what to expect. What do I actually want? An interval estimate is better. What do we mean by interval estimate? That means we would have a number on the low end and a number on the high end, and we would have something in between. That's an interval. So I want to somehow find out an interval that will allow me to say, this is what I believe about this population. So what I want to be able to create then is some way to construct an interval that's going to give me the information that I want. Another example. Let's say somebody asked me about lunch costs. I think we've done this example a few times. If I ask you the question, how much is it going to cost me for lunch if I stop for fast food on the interstate? If you say, well, between $0 and $100. Is that a correct answer? Listen?
Could be.
Okay.
It could fall in between those two numbers.
It seems reasonable that I'm not going to spend more than $100 if I stop for fast food. Yeah, it's kind of extreme though, right? So this is correct, but not accurate. Or I should say not precise. It's not good. Okay? It doesn't help me. But what if somebody says between $6.10 and $6.20? Do you think this person is giving me the correct answer? No. Okay? even though it is precise, that's, it's a very small range, but it's not correct, okay? Because you don't know that my lunch is going to be right in between those two numbers. So there's got to be a right size for an interval. There's got to be an interval that's going to tell me a correct value interval so that I can believe that it's true. And I want it to be as precise as I can get it. I want to have the interval not be huge, but I want it to be a size that makes sense and works. This is the idea then of the confidence interval. The confidence interval describes a measure of the population and I have my red marker right here. When I do a sample, that is not my goal. When I get a sample, I'm not done. I do not take a sample and say, great, I have a sample. The reason I take a sample is so I can say something about the population. If I were to say, I talked to 3 people and I found their average lunch cost was $20. Who cares, right? Those 3 people. Well, that doesn't help me. But if you say, I did research and I believe that I can say that anybody buying lunch would be between these 2 numbers or whatever, then that's going to be helpful for me. So I don't just want to get a sample, I want to know the population and I want to know what's about it. Now, as it turns out, even just finding the average of a population is not going to be easy. There's going to be variation involved, no matter what we do. But we're going to see how this works. So, let me give you a demonstration here. Here is a dot. I'm going to stand right here, and I'm going to try to hit that dot with this marker. Okay? Whoa, not too far away. Not too far away. I can do this all day. Am I going to hit the dot? Well, maybe if I scoot over a little bit. How long could I go without actually hitting the dot? I could go a long time without hitting it, okay? Now I'm going to use my folder. Did I hit the dot? Did I hit the dot? I could do this all day. I hit the dot every time. Okay? If I have a larger thing, I will be more confident of my results. So what I want to do is I want to consider if I have a larger interval, that will give me more confidence about what I'm doing. But just like I had over here, I don't want it to be too large because then I don't get good information. So how am I going to balance that out? What am I going to use for this? Well, I've actually got a formula that I can use to make this happen. And specifically, what we're going to talk about is the confidence interval for the population proportion. The population proportion is the same thing as what we've said before was the general probability. So, for example, I want to find out if people want to raise taxes in order to fix the roads. And I go out and ask people, favor increase in taxes. Now, there is a number out there, okay? There is a population number where there are people who say, yes, I want you to raise taxes. I don't know what that population number is. That would be the letter P. That's the symbol that I use for the general probability or for the population proportion. I don't know what that is. What I'm going to get is a sample. So in my survey, let's just say I asked 400 people. And I get, oh, I don't know. How many of you guys would be in favor of raising taxes to fix the roads? Okay, so let's say we had like 60, maybe. 67. It's certainly not the majority of people. Okay, so 60 people say yes. This is going to give me then the sample proportion. The sample proportion, P hat, is X over M, which in this case is 60 divided by 4. So what's that number? .15. If you don't have your calculator out yet, you will. This single number estimate that I have is not that great. Because if I ask a different set of 400 people, I'll get different answers. So I know that what I have right here is not the true value. It's not the value of the population. I don't care about this number by itself. I want to know what is the possibility that the population proportion is going to be something close to this. So I don't want just this measure of center. I want to be able to make an interval. And this is what that formula looks like. And this is in your textbook. It's also in the formulas and tables that are on Blackboard. So this is the formula for the confidence interval for the population proportion. Now we need to, of course, figure out what all these symbols are. Hopefully it's clear. P hat would be the 0.15. The P, which is in the middle, that's the thing we don't know. We're going to figure out what the number is on the left and what the number is on the right. But then we have to say, what do we want to figure out here? What we want to figure out is the width of that interval. Hi, Kathleen.
Hello.
This is Kathleen. Say hi to class. Kathleen's here to help.
I'm a math geek. I like to help when people get stuck.
Yeah, she's a helper. And she's supposed to keep me straight when I say something that's really weird,
Yeah,
but it doesn't always work.
I like to call them all for this.
Right. So, we're doing confidence intervals, clearly, Kathleen, and here's the formula. Right?
Okay.
Okay. So then, what we're going to say is, this thing here, this p hat q hat over n, we know that p hat is 0.15. Q hat is 1 minus p hat. So what would that be for this case? 0.85. Okay, so now I have p hat and q hat, and I know what n is. So I figured all that out, and I know p hat, but it's this thing that's really the weird part. Z of alpha over 2. And a lot of people get messed up because they think it's taking the z-score and multiplying it by alpha over 2. But that's not what it is. If I have z with an alpha over 2 over here, this thing here, this is a label telling me what z-score I want to have. So now we say, well, what's alpha? Alpha is a great big deal that we need to know all the time. Alpha is our chance of being wrong. So then, if I were to ask you, what kind of a number do we want here for alpha? Well, we would want it to be unusual for us to be wrong. So what does that tell me? I don't want to be wrong very often. I want it to be unusual. So what's my chance? What should that be?
5% or less.
5% or less. Now, as it turns out, there are 3 traditional values that we use for alpha. Alpha could be 0.10, 0.05, 0.01. Those are the 3 traditional ones, but almost all the time, we're using 0.05. Then, related to that idea is what we call the confidence level. If I have a 5% chance of being wrong, then my level of confidence would be 95%. So then I can have a 90%, 95%, or 99%. And again, these are based on statistical traditions, and they generally work, but we don't say it's got to be exactly 0.05 all the time. We could allow for some differences here, but it's convenient to say 5% is our alpha, so it's a 95% confidence that we have. So then what we do is we're going to use these ideas of the confidence to make our interval a certain size. And you've all written this down, I hope? You see that? So then the size of the interval depends on our confidence. So this is what we do. And the mathematics, I'm not going to try to explain everything of how this works. of why these numbers are here where they're supposed to be. But what we're going to say is I'm going to have a 95% confidence. That means I think it's going to happen 95% of the time. And this is going to be bell-shaped, right? It's got to be bell-shaped for this to work. And we're going to say, according to mathematics, it will. So I have a bell-shaped thing, and I want 95% to be where I expect the things to happen. So what would be my unusual areas here? Well, you know alpha is 0.05, right? But a confidence interval has two tails. This is another thing that you need to keep track of. A confidence interval has two tails. So that means we're considering that if we're 95% confident that's what's in the middle, what are the tails going to be? We're going to have to, that's correct, we're going to have to divide alpha by 2. Alpha divided by 2 is then 0.025 over here, and alpha divided by 2 is 0.025 over there. So in my formula, what I want to use is the z-score that puts me into those two tails. I want to know the z-score that goes here and the z-score that goes over there, knowing that my area is 0.025. Okay, any questions so far? Yes.
I'm super confused about this. Like, I'm confused about the alpha. Like, those are the only numbers that alpha will be just because,
Normally, yes.
like, that's, so we just pick one? And
You'll
put it
be
in
told
there?
in the problem which one you're going to use. Okay? So you don't have to decide which one to use.
So that's just the way it is.
That's just the way it is? No. Is it possible that the textbook author would say, let's use 0.02 for alpha? They could. They could throw that out there. But these are the ones that are normally used. And again, we want to have it be unusual to make a mistake, so we want alpha to be kind of small. Depending on the situation, sometimes we're really concerned about that, we go with 0.01. Most of the time, we just say 0.05. Sometimes we're like, let's just use 0.10. And we're okay with it. Right? Anything else? Okay. So what we're doing here is we're going to try and figure out how to predict or understand the value of the population proportion. So we need to get a number on the left side and a number on the right side. So far, we know what p hat is, we know what q hat is, we know n. We don't know the z-score to put into this formula. Remember, it's not that we're using alpha over 2 in any sense in the formula. Alpha over 2 is just a label to tell us which z-score we're supposed to use. So now, if I go somewhere and look at something, I'm going to be able to find that z-score, right? Where am I going to look to find a z-score that gives me 0.025 in the area?
Negative 1.96.
Okay, negative 1.96 on table E will give me that area back. Now, because the bell-shaped curve is the same on both sides, this is going to be positive 1.96. So that'll work on the other side. The meaning of this thing right here is that we are controlling the amount of variation based on our formula. So that we're going to say, I know how wide to make my interval in order to get this specific amount of confidence. So if I use these numbers and put them in here, then I will be 95% confident about the population number. So I started with the sample, but once I put my stuff in here, I'm going to get something about the population. So the nice thing about this, okay, is that if we're normally using these three things right here, we don't have to keep looking them up over and over again. We know that for a 95% confidence level, the z of alpha over 2 is going to be 1.96. So we know that, and we have that, and we don't have to keep looking it up. So that's good. Now, I want to try and make sure I get this correct from the textbook so that when you do your homework, you'll be able to see this. Because, as we said earlier, the things that we're doing here, all these table numbers, they're actually rounded off. You don't have 7 digits of accuracy in these table numbers, right? And so when you say, well, I want to know what this number is, we're not getting exact numbers, and that's going to be okay. Because remember, the next time I do this, it's going to be different anyway. So I'm going to go to my page here to find confidence intervals. And if I go to section 3, by the way, the textbook does not start with this formula in chapter 7. It starts with a different one, but this is where we are going to start. Okay. So when we look at these z-scores, then we're going to have the 1.96 for this one. And I thought they had a nice little table, but I don't see it. So let's see what we can find. What do we find for 99%? Well, if it's 99%, that's 99% in the middle. We take alpha, which is 0.01, and divide it by 2. So that's 0.005. If I look at table E, I want to find an area number of 0.005. What do I see? Negative 2.58 or 7. Either one will be all right. Okay? And so then, on the other side, be positive 2.57. What if it was 90%? That would be 10% divided by 2, bless you, which is 0.05. So I want to find the z-score that corresponds with alpha over 2, which is 0.05. What that would mean is that you have your E table out and you're looking in the middle of the table at percentages. What do we have that's close to 0.05?
1.64.
We have 1.64, and we also have 1.65. Those would both be possible. So 1.64 or 1.65. When you do this homework, all right, the software is supposed to allow you to do either one of these answers. Okay? You might want to check, view the example, just make sure that they're doing that. It is certainly possible we could pick 1.645. That would also be nice. Now, I don't want you to lose sight of the purpose of what we're doing here. What we want is to come up with numbers that are in this formula that I wrote up here that make the size of our interval based on how much confidence we want to have. If I want to have more confidence in my result, I'm going to have a larger interval. Now, what normally happens here is that there's a lot of numbers in this formula, so you have to be kind of careful about how it works, and you have to make sure that you do not subtract until you do all the multiplying. Okay? You do not take this minus this and then multiply. You have to do all this square rooting and multiplying and then do the subtraction. All right, so let's actually make this happen. I'm going to use a 95% confidence interval. So I'm going to have 0.15 minus 1.96 times the square root of 0.15 times 0.85 divided by 400. Now, if you'll notice, the thing that comes after the subtraction sign is the same on both sides. So we don't have to figure it twice. You just have to figure it once. What's relatively common here is that people look at this and they say, wow, that's a lot of numbers. So what has to happen is that you have to use your calculator to do this calculation. Different calculators have different order of how they do things. You need to be familiar with how your calculator does this calculation, all right? So I want you to find out what these numbers are going to come out to be. All right, so check your neighbor's stuff, see if your neighbor's stuff is good.
So the number that you got, you multiply it by 1.96, and then you take 0.5. I guess you have. When I took that times 1.6. Because that's what I put that first.
Okay, so once again, I'm going to write this up here. This is a 95% confidence interval for the proportion. Emily, you got something you like there?
0.115008 and then 0.184992.
Okay. Now, if we were to ask the question, how accurate do we think these numbers actually are? This 1.96 is only accurate to 3 digits because we had to round off the stuff on the table. So in this case, we would want to go after the decimal point to 3 digits, probably. So then we would say that this would be 0.115 on the left side and 0.185 on the right side. Now, it's really pretty important that you can make this happen, right? So if there's anything happening out there that's bad, we want to fix it. So does anybody have any question about these two numbers? 115 on the left, 185 on the right.
How do you get those numbers?
Okay, so we're going to start by taking 0.15 times 0.85 divided by 400 and take the square root. So we're going to do the thing that's in the square root first. Okay. Now it is important to not round this number off once you get to it. Okay. So Elena, you got something for me there? Okay.
Are you looking for?
I'm looking for what happens after you take the square root. What is this part of this?
I got 0.017853577.
That's correct. Okay. Zero, 1785. Okay. So then I'm going to come back to okay. What you should do there is just hit the OK. Now notice, the square root puts a parenthesis in here, so you don't have to put a square root in here. Okay? Okay? Some calculators automatically put a parenthesis after the square root, some don't. But this has to be done all within the square root, okay? So does anybody else have a question about this number right here? So once you get this number, you multiply this by 1.96. Now you don't have to write this number down necessarily. You can if you want to keep track of your steps. But if you just take this and multiply by 1.96, then you get 0.34993. More or less. Okay? So this is 1.96 multiplied by this number, which came out from the square root. Then once we have this number, then we're going to take 0.15 minus this and 0.15 plus that. And that will hopefully give us those results right there. All right, so it's definitely something that we want to fix if it's broken. All right, so if it is broke, do fix it. So does anybody have any question about getting these two numbers right? Okay, now we have to ask the question, what do they actually mean? I have two numbers, 11.5% and 18.5%, if I write them that way. What is this actually telling me? This is describing for me the population proportion interval. When I did my sample, p-hat, it was 15%. Those 400 people told me they wanted to raise taxes. No, but actually it was 60 out of the 400, right? So those 60 people out of the 400, they told me that they wanted to raise taxes. That was a 15% number. I know that 15% is not really for everyone. It's just for those people. What do I think is true about everyone in general? Well, from this formula, based on what I just did, I believe that the actual population proportion is between 11.5 and 18.5%. This is what I would expect the population proportion to be. So the mathematics here are allowing me to say, if I talk to a bunch of people, I can now look at everybody and say, I'm pretty sure that the proportion will be between these two numbers. Now, how helpful is this? Well, you might say, I got 15% for my survey. It's somewhere between like 12 and 19%. It's pretty clear that this is not popular, right? People don't really want to raise taxes. Okay, I understand that. But it is a certain amount of the population, right? So there are people who think I should do this. It's not the majority, but this gives me a pretty clear idea of how many people out there want to do this thing. Now, you can see how this would apply to pretty much any kind of question we can ask. Have you experienced dizziness in the past 3 weeks? Do you like to go to water parks? Have you had a visit with a psychiatrist? All of those things, you can ask a simple yes or no question. You can get a proportion of people from your survey. And then, according to this, you can make that statement about the entire population based on just a sample. Now, recall, in statistics, we don't ever actually believe the things that we're saying completely. What is true about these 400 people might not be true in general. My sample might be messed up. There's all kinds of things that could happen here. But this formula is controlling the sample variation to the point where I am able to say something intelligent about everybody even though I only talked to 400 people. So that's good. Now, what would happen if I changed this to be a 99% confidence interval? Let's just move it over here. Let's say it's a 99% now. Nothing else changes except the z-score that I'm going to put in here. So what I want you to do is to refigure this, but now using a z-score of 2.57 instead of 1.96, and see what happens. Work. All right. All right, check that neighbor of yours, see what they're doing. See if they've got good numbers.
No, the big number. Zero together. Yeah, it's just the same
All right, Casey, you got numbers for me here?
0.104 and then 0.196.
Okay. So what happened? We became more confident about our results. So I'm more sure now that this interval is correct. But in order for me to be more sure, my interval has to be bigger. So now it's not just from like 12 to 19, now it's from 10 to 20. Is that a lot of difference? No, not really. So in many cases, a 99% and a 95% are not really that much different. So it doesn't really matter that much which one we take, as long as it's somewhere in that neighborhood. So yeah, there are times when the 95 versus the 99 is a big deal, but a lot of times it's just not a big deal. So if we say, well, which one should I use? Should I use 0.05, 0.01? Well, how about you just do both of them? It doesn't matter. Doesn't matter. The fact of the matter is the information that we're getting here about how many people are in favor of taxes. If you say, well, is it 10% or is it 20%? Does that make a big difference to anybody? I'm not sure. So there's a real question about whether it's practically significant or statistically significant. Just because we prove something using statistics doesn't mean anybody cares, right? But if we were doing something like side effects of medicine, and you say, well, how many people are going to have to go to the emergency room? Somewhere between 10 and 20%. Like, oh, that's a lot of people. As opposed to who's going to vote for taxes, no big deal. All right, so what's going to happen next time we get together is that we're going to talk a little bit more about this with proportions, but then we're going to have a different equation for the averages, and then we're going to have a different equation for the standard deviations. And so it's going to get pretty complicated pretty fast. So that's why we're kind of taking it easy. We're not going to have any homework due right away. Of course, if you want to work ahead, that's beautiful. Feel free to do so. All right, so we're going to take a 10-minute break here, and then we're going to come back and have our exam. That'll be at 1:50.
I have a question on our practice exam.